SwayamPrabha. Digital India. Educated India.
See, we were discussing about George Calais' explanation for generation of lift. We'll just quickly revise so that we can understand few things better. Remember, this is the plate, and if I move this plate at an angle with respect to the speed and this angle, because of this angle, there will be pressure from the air outside as it moves like this, and that will get translated into force because of this area, and there will be normal force acting on this body. So I represent this as, this is the pressure because of air as it moves through the air, and resultant of this I can write this is R, the reaction, and one component perpendicular to velocity we call it lift, another component which is opposing the velocity called drag, and this lift is supposed to balance the weight. And if I put an engine which gives thrust, so this thrust is supposed to balance the drag so that I can move like this, which is typically, you'll see soon we'll be defining this flight as a cruise flight. But let us understand first that if lift has to balance the weight, then what is this lift? This lift is generated because there is an angle between the velocity vector and this surface, and this angle we call, let's say, alpha. This lift definitely will depend upon the speed. It will depend upon the area of this plate. When it comes to the area, we also now let us investigate one thing. If I move this plate like this, or I move the plate like this, both are having same angle, but which case you think more lift will be there? This way or this way? This is this way or this way. It's obvious that lift will be more when I'm moving it like this. That means it's not only the area, but also how the area is laid out with respect to the velocity vector. You will see soon we'll be defining some term of this piece in terms of aspect ratio. Watch out for understanding what is the meaning of aspect ratio. And before we go for aspect ratio, we will have a relook here and try to see how do I translate this to a pilot in terms of flying the machine. Because I always said, whatever aerodynamics, whatever flight mechanics we do, finally I have to translate this in terms of a language which a pilot can understand. Right? Then from here we realize that we will be operating in terms of CL, which is nothing but lift getting non-dimensionalized by dynamic pressure into S reference. And when you say the dynamic pressure, we talked about free stream dynamic pressure, because we realized that the velocity at different point will be different. If it is an aircraft, if it is moving like this, velocity here, velocity here, velocity here, or the dynamic pressure here, 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 all will be different. So when I non-dimensionalize this, which dynamic pressure I take? So for that, we choose free stream condition. The meaning thereby that at this condition is not affected by the presence of the body, and that is what is half rho v square free stream dynamic pressure, and S is the reference area. By now you know that S is the wing area for aircraft, right? Similarly, CD, we have drag, non-dimensionalized with dynamic pressure, again free stream, and wing area, right? Now let us see. If I want to fly a machine, and if I decided to operate in terms of CL, then I will say for a given weight, given rho, the given altitude, and given speed, the lift is equal to weight, and lift is nothing but, from that expression I see it is half rho v square S CL equal to weight, or CL equal to 2W by rho v square S. So what I know, for a given weight, if I want to maintain lift equal to weight, I must fly at this CL. But then, how do I generate this CL? I will be turning this plate at an angle or turning the airplane at an angle, so that total CL of the aircraft is what is dictated by this CL. And how do I do that? Because I know the airplane have wing, has tail, and at angle of attack they produce lift, the fuselage produce lift, the total lift and total CL should be equal to the CL required. This part we have already covered. In covering this, we also have spoken about the finite wing, and quickly I'll go through that. Finite wing we understand. This is typically a finite wing where this is the span and this is the chord here. We have already discussed if I joining a line, the leading edge and the trailing edge, the straight line is the chord, and this is the span. And if it is a finite wing, then what is happening, that at an angle of attack, when there is a lift, this bottom portion is high pressure compared to the top portion, so there are vortices will be formed, and that has two effects. One is because it is carrying out rotational kinetic energy, and that energy has come from the energy of the machine, so the machine will lose energy, or it's increased drag, and that is termed as vortex drag or lift induced drag. And second thing, as the vortices form like this, they induce a downwash in the downward direction. The meaning thereby, if this is the free stream velocity, as it comes close to the aircraft, its velocity vector gets tilted because of downwash component. So if I try to draw that, so finite wing, before I draw anything, quickly I should have my thinking clear. One is vortex drag or lift induced drag. Another component is induced downwash. So the local velocity is tilted, right? Okay. Just to draw a diagram on this, let us see. This is the wing, and this is the free stream speed or velocity. As it comes close, there is a downwash, so the velocity vector no more remains straight like this, they also get tilted like this. And this tilt, if I try to draw, that is nothing but this is the free stream and this is the downwash denoted by W. Then this is the resultant velocity vector which comes because of the downwash. Please note that this is the free stream velocity, and the free stream velocity gets superimposed with the downwash because of wingtip vortices, and the velocity vector gets tilted. So local velocity vector is different than the free stream velocity vector. Now the question is, when I try to find lift on this wing, the lift will be perpendicular to the local flow condition. But we define drag and lift of the whole airplane based on free stream condition. This is very important. This is to be noted down. The lift on the wing or any component will be perpendicular to the local velocity. However, CL of the whole aircraft, when I try to write the CL or the lift, when I try to model it, I should ensure that that lift is perpendicular to free stream velocity. And by now you know the local velocity and free stream velocity, they are not in same direction because of downwash near the wing or near any other component. In this case, we are discussing downwash because of the wingtip vortices. That is, as these vortices go like this, they induce a downwash, right? So let us try to use this understanding and try to get an approximate expression for the induced drag. Let's say this is the lift of this is the wing, and this is your free stream velocity direction. And because of downwash, this direction has changed, the local, V local. Now here, if I try to draw lift, I know this will be perpendicular to the local flow condition. This lift seen by the wing will be perpendicular to the local flow condition, not to V infinity, right? And this angle is called this angle that tilt in the velocity vector, which is called induced angle of attack. Who has induced this? It's induced by the downwash. Why downwash has come? Because of vortices. Why vortices have come? Because of pressure difference in the bottom and the top portion. Why? And why do you need a pressure difference? Because I want lift, right? So it is alpha induced. Now, since I want to define lift and drag, so if I want to write lift, I have to resolve this lift, which I will call it local for clarity. That should be perpendicular to the free stream direction for the overall aircraft. So if I take the component, so this is the lift and this is the drag. Okay. So if I now try to write the drag, you see this will be L sine alpha I, this component, right? I write di, this is nothing but L sine alpha I. And for a small angle, I can write this as L alpha I. That is for small angle, sine alpha I approximately equal to alpha I, right? Similarly, if I can write this equivalently, CD equal to CL into alpha I, where CD, when I am writing like this, please understand, I am talking about induced drag coefficient, right? Because it is coming from the lift. And from theory of incompressible flow for elliptic distribution, one can show that alpha I can be approximated as CL by pi aspect ratio to E. Of course, E is 1 for elliptic distribution of lift per unit span. That is, if I draw it, you'll find this is typically elliptic distribution of lift. Any standard textbook you can get this information in detail, and the bottom I am writing those downwash component and denoted by W, right? And of course, E is less than 1 for anything which is not non-elliptic. Mostly we have non-elliptic distribution, right? Now if I substitute this here, so what I get? CD equal to CL into CL by pi aspect ratio E, and that is equal to CL square by pi aspect ratio E. Okay? So this is nothing but CDI, CD induced. So now for a wing, what do we see? For a wing, if I want to find total CD, I know total CD will be what? One part is induced because of lift, which is given by CL square by pi aspect ratio E. And what about the other part? Suppose this is the wing, or for that matter, this is the airplane. As I am allowing the air to flow over the wing at alpha equal to 0. So there will be a lot of resistance because of skin friction. Depending upon how streamlined it is, the skin friction value will change. There could be flow separation at different points. So there could be pressure drag because of flow separation. So a typical resistance which will be at alpha equal to 0, and typical resistance because of lift. And the typical resistance for alpha equal to 0 we call parasite drag, which are dependent on the flow condition, whether it is subsonic, low subsonic, supersonic, very high speed. Depends upon what is the geometry of the airplane. You will know in aerodynamics something called Reynolds number, which talks about ratio of inertia to viscous force. That is, if it is a low Reynolds number, you are expected to have more viscous effect, right? So accordingly to that, this CD naught will be decided, and once we say CD naught, this naught means at CD at 0 lift. For a symmetric aerofoil, it is good enough to say CD at alpha equal to 0. For cambered aerofoil, we define this, we write CD at CL equal to 0, and as we progress, we see that sometimes we try to represent this drag coefficient using CD minimum also. Those are a matter of detail. At this present, only understand that the drag coefficient will have two components, one because of parasite drag, zero lift drag, and the lift induced drag. And this representation is known as drag polar. Whenever you finalize the design, when aircraft is flight tested, everything is done, then this has to be estimated, and every aircraft is benchmarked with a given drag polar under different flight conditions, right? So this is one of the contribution of finite wing, that because of finite wing there is vortices. Because of vortices there are drag, say induced drag, and because of vortices there are downwash, which will also change the lift curve slope or CL alpha of the wing. Let us see how that happens. Let me draw this diagram. So this is typically, let's say this is a wing, and this is the free stream velocity. As it comes near the wing, there's a downwash because of wingtip vortices. The velocity vector gets tilted downward. So this is the local velocity direction, and this is the chord line. All these things we are now familiar, and this is the angle, which I call it alpha effective, because as far as this wing or the body is concerned, all the lift generation will happen because of this angle. Because come back to the George Calais, that the lift will depend upon the angle between the velocity vector, local velocity vector, and the surface or the chord line in this case. So this is alpha effective, and alpha is the induced angle of attack. So now we understand one thing. If I denote A0 as 2D lift curve slope, that is lift curve slope, which is typically CL alpha, represented by CL alpha. What is the meaning of this 2D lift curve slope? That we are assuming that span is infinite, so there are no alpha I, because if it is infinite, that means there are no wingtip, it's not a finite wing, so there won't be any wingtip vortices, so there won't be any downwash, so there are no alpha I. Okay, so that is what is A0. So if I now write dCl by d alpha minus alpha I, this should give me A0 because I have taken out alpha I from the angle. This slope, when I am writing CL versus alpha effective, which doesn't have alpha I, or alpha I has been taken out, the effect is taken out, we are talking about only this. So this should be the A0. If that is A0, then I can write CL equal to A0 alpha minus alpha I plus constant. Okay. So CL I can write as A0 alpha. For alpha I put the expression which I have written earlier, which is CL by pi aspect ratio E. I multiplied by 57.3 to convert this value from radian to degree, right? And then plus constant. So if I now manipulate this, do some algebraic adjustment, I can find that CL equal to A0 alpha by 1 plus 57.3 A0 by pi aspect ratio E. Okay? Or I can write dCl by d alpha equal to A0 divided by 1 plus 57.3 A0 by pi aspect ratio E. Let us see. Again we come back here. What was A0? A0 is the lift curve slope for an aerofoil, that is 2D value, right? That means the 2D value doesn't have any alpha I. So when I'm trying to find out slope CL and angle of attack, I am eliminating or taking out the contribution of alpha I. So if I take this slope, this should be A0, right? Now from here I write CL equal to this, and I get an expression CL equal to this A0 alpha plus 1 plus 57.3 A0 by pi aspect ratio E. 57.3 I put to convert radian to degree. So what is the message here? If I have got aerofoil lift curve slope, let's say 0.1 per degree, it is degree, that's a per degree I'm talking about, then if I want to really calculate CL, what I have to do, I have to use that value, put alpha in degree and all such values A0 here. So from 2D value, I'll get 3D value. In this whole expression, there is a one term which I am being writing A, that is the aspect ratio. We need to know what is this aspect ratio. Remember, we'll go back again. If this is the plate and I'm flying like this, as per as George Calais, the lift will be, because there is an angle between the velocity vector and this surface, and the lift depends upon the reaction, which depends upon velocity, area, the density, etc., etc. If it depends upon area, then whether it goes like this or it goes like this, they should be same, but they are not same. We know that lift, for generating lift, I should fly like this. Very simple way to get an understanding of it. Remember, when I'm flying like this, I can assume that it is composed of so many aerofoils like this. But if I'm flying like this, I'm having aerofoils which are not as large as aerofoil like this. Because why aerofoil? Because the pressure difference will come because of contour of the aerofoil. And here, if I'm flying like this, so many aerofoils, so the contour will get, effect will get added, and we get lift. To make sure that we are flying like this, we also define some term called aspect ratio, and that gives us a feel which way I am orienting, this way or this way. For example, aspect ratio, if I draw a wing, if I call this B as span and this C as chord, aspect ratio we define as B square by S fin or S wing. Okay. For a rectangular wing, it automatically becomes B square by B into C, so it becomes B by C for a rectangular planform wing. Rectangular wing, which I mean planform. Now see, if this is the wing, if the span is increased to infinity, what will happen to the aspect ratio? So aspect ratio also will become infinite. If aspect ratio become infinite here, what happens here? If aspect ratio becomes infinite, very large, then this term will become 0. So in that case, the CL will be same as CL what you get from 2D. Or coming here, the CL alpha of the whole wing will be same as CL alpha of the aerofoil. That is, it will now behave like a 2D. So if you want to get larger CL alpha, it is better to have larger aspect ratio. But there is a problem of larger aspect ratio. One of the problem is if it is very large aspect ratio wing, how do you balance the weight of the wing? And there are other issues will come as we progress, you'll understand. So in a nutshell, whole effort here is towards making one thing very clear, that if you have a finite wing, it will give induced drag, and there, because of induced drag, your drag coefficient will have CD parasite or zero lift drag plus KCL square. This typically follow a parabolic form, and also the lift curve slope or CL alpha of the wing will also reduce as compared to CL alpha of the aerofoil. If you understand this, then we have understood what is minimum required for and using this concept for performance analysis. Why do I need a relationship between CL and alpha? Remember, we have written CL equal to CL naught plus CL alpha into alpha. Why do we require this? Because to maintain lift equal to weight, we need some CL, which will be given by the lift equal to weight equation. But for a pilot, he has to generate that CL, so he has to turn the airplane by some angle of attack, which will be dictated by this relationship. And finite wing, we were trying to understand with aspect ratio how CL alpha of the wing is going to change, right? So this is good enough understanding for us to use this for performance analysis. We may, most likely we are going to start with the cruise performance next. Thank you.